Hi, welcome back to another episode of, well, it's not Programming with Tim, but I do want to talk about programming in a video where I'm just talking and not programming because it's kind of an abstract idea. You see, I took a lot of mathematically related and coding intensive classes when I was in school. But there was a class that a lot of people liked because they thought it was really in depth and smart and wise about how to code the right way. And it sort of had a lot of good points. Now, I had been experienced with at least being aware of and doing something with coding and mathematics since I was young. And I was taking this class when I was like 25 years old. And the class had some good points. And it even reminded me of some of the things that my dad would try to teach me too. And there's some good to it, but there's also you ever notice that sometimes there's rules and there's laws and it's like, I kind of get why they wanted to make that law. I kind of get what the purpose of that rule was, but it's not inherently eternal. It's not the end-all solution. It's not the best solution. In fact, if you were for thousands of years to just keep following that rule or that law, eventually it would turn against you and it would actually limit you. And that's how I felt about this class. To me, it was frustrating because I felt like the class itself was in a way a bit lazy in the sense that to me, mathematics is not lazy because it makes statements which are proven, and then when they're proven and known, they're eternal. Like, they might not always be the most useful statement, but you can depend on them. They're propositions that just last forever, and whether or not you specifically use a certain theorem or not, or a certain logic system or something like that, at least it's true, it's dependable, it's always 100% true. But these were ideas and laws that were based on concepts which were true, like abstract ideas which were true, such as, let me give you an example. You should always comment your code. You should always make it explicitly clear with variable names and functions. Oh, and by the way, functions should only be like 4 lines long. And if it's longer than that, you should try to take part of that and kind of put it in its own function. That way you can name it, and then maybe if you need to reuse that code again, you can reuse the code again. Now, what's funny is the logic and the thinking behind those statements is really, really important. Like, it's actually really good ideas, like super, super important. And they're actually related to mathematical ideas such as lambda calculus and the mathematics behind the programming language Lisp and a lot of other academic languages like Haskell and things like that. But the actual advice of make sure you put comments in your source code, well, that assumes, first of all, that what you're editing is text, and that's more optimal to edit source code as text than it is to edit a parse tree. Okay, which to me, that's not proven at all. In fact, I would say that with the right type of tools and the right type of filtering, it's actually more effective and more efficient to edit a parse tree than to edit text. And it's also important, it's also to me not clear that just because you express something, like you re-express something in English, doesn't mean that it's more effective. Like, for example, if I have some code snippet that says, well, x equals x plus 1, okay? I can put a comment and say, well, I'm going to increment x, or I'm going to add 1 to x, or something like that, okay? Well, okay. So I'm explaining what I'm doing. And let's pretend that maybe I'm doing something extremely clever. Maybe I have some really in-depth recursive statement. And then I explain, oh, I'm just iterating based on the Collatz sequence. That's all. Okay, well, it might be hard for them to backtrack using the code what I'm doing, but they can see in the comments, oh, he's clearly doing that. Okay, great. That's super helpful. And that's a true statement. But there's an issue with it. It's not a complete statement. It doesn't express all things. It's not eternal. Because I'm going to explain why. Imagine if I started producing lots and lots of software, and thousands of programmers started producing lots and lots of software. And they all wanted to share software, and they didn't just have compilers, but they also had tools that verified consistencies between the software expressions. So if you had a function that did the exact same thing as my function, for example, your function might say, well, A equals A plus 1 recurse on B. And my function does X equals X plus 1 recurse on Y. And it turns out that the A and the X are really the same, and the B and the Y are really the same. And so when you compile it down, they're really doing precisely the same thing. But in English, he kind of wrote his English a little differently. He put an apostrophe and I didn't. And he capitalized something that I didn't. And he put something in two separate sentences, which I put in with a semicolon, and then I referred to something that didn't have to do with the context that he was solving his problem in. And so I said, well, I recurse on the Collatz sequence on my code. And then in his code, it says, well, I use the Collatz sequence to solve X and X problem. Okay. So now we have two pieces of code which are very similar. And in some contexts, they're functionally identical. And so you should be able to run some kind of hashing algorithm and see that they are the same in some sense. And their comments will be different. And now if you try to store them in a database, the database will have to refer to them separately and show that there's differences. And if you try to update one of them to do something different and then save it, then now you have to figure out that they're not really the same anymore. And you want to question whether you want to update the other one or not. See what the problem is? So the concept of having well-documented code and things like that, that's kind of a good back-end concept. It's like a higher level abstract idea that makes sense. But it doesn't mean that but that's assuming that you're going to make a classical program. You're going to say, I'm just going to make a typically sized and typically complex C program, or typically sized, typically complex, not necessarily using unbounded recursion or generating larger hierarchical logic systems or anything like that. I'm just going to make the typical C++ program. Then it's fine. Then it's like, okay, for typical programs in that time period and that type of context, using that type of operating system and that type of logical thinking to solve that types of problems in that kind of area of the universe, then sure, comment your code. But to me, it's like, no, like, and all my math classes were different. I didn't have a problem with them because to me, it didn't matter whether you're talking about set theory or type theory or things like that. To me, it was just like, well, you could apply this in many different ways. You could apply set theory to types. You could apply set theory to the integers that you're dealing with. You could apply set theory to the objects that you're referring to and things like that. And all of the properties hold. All of the mathematical properties hold. And so as soon as you have an inconsistency in set theory, well, that's a self-defining inconsistency. It's not making the assumption of how you're applying the solution to the problem. So my dad, I'm kind of different in thinking from him. My dad is very brilliant. He got high honors in school. He studied electrical engineering, and he would design chips, and he would try to convince over probably 20 years ago, He would try to convince a company to start training their employees more on automated hardware checking tools, because they used to check them by hand, and he liked the software to check them with. And his boss would be like, don't do that, it's a waste of time. So in many ways, I'm similar to my dad, but I remember some things that I sort of just disagree about when it comes to like your base philosophy. Like, for instance, my dad kind of made the assumption that, okay, if you're going to cut the grass, okay, and I'm not saying this is like totally a bad thing, but I'm saying that that it's kind of a hack in reality, okay? So when he says, when you cut the grass, you can cut it in nice, neat rows. And then that you kind of get the job done. You're doing a good job. So cut the grass. When you mow the lawn, cut it in nice, straight, even rows. Now, it might sound very agreeable. It might sound like, oh yeah, cut the grass in straight rows. It makes perfect sense. I mean, it's organized, it's efficient, it seems like it makes sense. But that's the problem. It just seems like it makes sense. It's not very explicitly proven that, like, oh, this definitely 100% of the time in every possible case is always better. And you might be like, oh, well, you're just being picky. Like, cutting in straight lines, you should just agree with him, because in most cases, that's what matters. Does it work most of the time? Yes, kind of. But no. You see, it depends what class of problems you're trying to solve. Like for me, I'm not just trying to solve some generic, make a little game and then move on. I try to come up with new programming languages. I try to search out all possible programs that you can create given a language. And there's a very, very big difference between, like, let's say, 64 to the 1000th power number of programs and, like, I don't know, 1,000 combination, 1,000 programs or something like that. The combinatorics go way up if you're going to search through every possible character combination just to see if it's a valid program, versus given a programming language which has an explicitly defined grammar, which you can inductively produce only valid programs to then test. And so when it comes to cutting the lawn philosophy, do you need straight lines, perfectly straight lines? And the answer is, well, it depends. If I'm going to cut a giant, circular lawn, maybe it's faster to cut straight lines, but remember, I'm going to have to turn every time I go through. So maybe it's faster to do a big spiral. Maybe. Not really sure. Or maybe I have a lawn where I have a lot of trees that I have to keep going around, and there's a certain path, there's like an S path where I can kind of go around that, and maybe it turns out to be more efficient. Because my base rules can exist. That's the problem. Some people think that you can't define these things, but some of them you can. And it's not always going to be harder. It's not always going to be impossible, and it's not always going to be like NP hard. It's not going to be exponential to solve some of these like optimal cases. Sometimes it is. Sometimes it definitely is, and I give you that. Like, for example, the A-star algorithm. If you want to search for the closest path to your enemy, it is extremely expensive to do the optimal path versus the A-star algorithm, which gives you like a 95%, like best path, but it's super cheap, super fast. So cutting the lawn in straight lines, it's a valid thing to follow. In fact, it's probably good practical advice to follow, but I just feel that in some sense I trust people in a way. I trust people that their advice is golden if they say it is. And to me, there's different levels. You want to give a good advice, but then you also want to say why. And what's funny is I concluded this to be so true that I thought maybe this has to be true, like in the Bible too, like because it seems like every time I think somebody should always do this, because I almost proven that it's better to do it this way. Like I've pretty much proven 100% that this is actually is better to do things this way. And it turns out that's how some of the laws were actually given back to the Israelites, is they were given laws and then they were told why those laws are important. So it wouldn't just be thou shalt not do this, but it was you shouldn't do this because this is why. You should treat your neighbor with respect because they live next to you and they trust you, and it kind of provides some context, because that every piece of advice sort of comes with a context. You can't really separate it from the context, because if you could, then it actually would be math, because it would always be true. It wouldn't need a context in order to make it true. So when it came to the class, a lot of people liked the class. The teacher taught, don't just write clever code. Well, write well documented code. And it was good advice when if your mindset was otherwise to do things a very poor way. Like if your mindset was to, well, I'm just going to write garbage code, I'm going to make it really hard to re-understand what I was going to do, and I'm going to make it really hard to work with other people. Okay, then the advice kind of applies really strongly there. But people misunderstand things then. Because people will, on top of that advice, people still use wrong logic. Like, people might think, well, Lisp is an old language, therefore Python, since it's newer and used more, must be a better language to solve any problem. No. No. Actually, Lisp outlasted pretty much any other language. And there's a reason for that. There's mathematical reasons for that. And so you could argue that maybe it's better than other languages, because the fact that it's lasted that long. So it depends what problem you're trying to solve and what is the context of how you're defining the problem that you're trying to solve. Are you just trying to solve a specific algorithm given a certain amount of time and you don't care about the long-term effects? Or are you worried about the long run? And a lot of times, problems that I try to solve, I am thinking about the very long run. I'm thinking about to infinity and beyond. How, looking down towards the future, not a specific point in time, but all the way down. Like asymptotically down. As far as you could see at the convergence point, where there's no fixed date. I like to think like that. I like to think about far down in the future, and it causes people to think to misunderstand things, and then they just think that I'm dumb, or they think that I am stupid, that I don't know what I'm doing, that I am crazy, that I won't admit that I'm wrong, that this or that. They'll think all these things because I'll make statements that contradict what they determine is optimal, what they determine works well, what they determine is efficient for the short term, or to what to them seems like a pretty long term. Because to them, 10 years, 100 years, 1,000 years, 10,000 years, that's really far out. But to me, it's just like, no. 10,000 years is nothing, because to me it's how do you create something that is sustainable for the long term, and to me the only thing that really does that is formal mathematics. That's the only thing, because that's the only thing that you can clearly define the context in which it holds. And when it holds 100%. And when it doesn't hold, you have a clear context to tell you that it doesn't hold. So that's what's beautiful about it, is it maintains itself into the future. And that's part of the reason why I like math and computer science combined as topics, because they work well in that sense. They work well in the sense that they're scalable. And you have to think in that way if you want to create new programming languages and new things like that, because it's not easy. It's not easy. You can make it good in 9 out of 10 ways, and then if you totally fail in that last 10 out of 10th way, like it's really inefficient to write programs, or it's really inefficient to edit programs, or it's really inefficient to learn how to use this logic system or something like that. Like if you fail at some point, then your system sort of just breaks down. So that's why it's not easy. And that's another thing that my dad would say is there's always a give or take. Like you're either gonna get leverage or you're gonna have to do a lot of or you get speed or something like that. Like he said that there's a give or take between two ideas, and my response to that is yes, if you want to be just a quote unquote good engineer. If you just want to be a good engineer, then you'll try to balance things like that. But if you want to do your best, you'll search out and try to find solutions that solve all the problems. You'll try to come up with a solution that, the electric car problem, the pizza problem. Can you get cheap and fast delivery and high quality pizza? Can you get all three of those put together? Can you get an electric car that is more efficient with energy, that does cost less, that is economical, that is safer? Can you get all the variables in your favor without having to have this glaring variable that's just like, well, the only catch is that it costs $10 million. Well, the only catch is that there's a 60% chance that you'll die. Well, the only catch is that it's 10 million times more inefficient to manufacture. That's what is the catch? There shouldn't to get rid of the catch is actually a much trickier problem. People can come up with cool ideas all day. Don't get me wrong. They came up with Haskell and they didn't even formally define it, and yet it was a powerful computational tool that they couldn't even print hello world in. They couldn't even print hello world. Okay? But it was an amazing programming language from, when we look back at it, because it had some really cool mathematics behind it that made it really powerful, that made it so you could parallelize it, that made it so that you could do computations with it that were really efficient, that made it so that you could define problems well so that they didn't have bugs and things like that. But if you can't print hello world, then it shows, wow, that if they couldn't even do that, I mean, that's glaringly funny for people who are used to learning a programming language like BASIC, where that's the first thing you learn is, hey, you can just call this command called print. So, cutting the grass in straight lines. It's better than just being some lazy drunkard who doesn't like to cut their grass at all, or who doesn't have a good attention span and they just don't have the mind to be able to focus and just solve any problem in general. That is true. But it's not a mathematical statement. That's the point. So there's good practice to keep yourself in check, to make sure that what you're doing makes sense. And then there's also mathematics. And mathematics kind of brings things to another level, and you have to be able to differentiate between the two. Because sometimes somebody may be making a decision and you might just think, well, they're just inexperienced. Well, they're just new. Well, they just don't know what they're doing. Well, when really they're making their decisions because of mathematical principles. And that's really what's happening behind the scenes. So you have to be able to differentiate between that, and you have to be able to tell the difference. So Coding. I might not be this expert coder who everyone thinks is, oh, this guy is a super hacker. I'd rather not be known for being a good hacker. For being someone who can throw code together to just do things. Now, I do want to have fun, and I want to be able to do stuff like that. But I want to make something that's genuine and useful and will work, and what will be built upon and isn't false, isn't something that everyone thinks is good, but in reality doesn't help. So, yeah. Let me know what you guys think, and if you've studied neural networks before, let me know what you think about those. If you've studied or heard about genetic algorithms, let me know what you think about those. And if you've thought of ways of combining those algorithms together in sequence or in using neural networks to guide the creation of genetic algorithms, or using genetic algorithms to kind of guide the breeding of different types of neural networks that are parameterized differently. Let me know what you think about that, because if you think about these higher level topics and these abstract ideas, and you're like me, you can kind of get carried away thinking about them a lot without actually testing them and seeing if your ideas work, and making sure that things are formal so that it's not just some crazy idea, but you can build upon it because you know which ones are sensible and which ones aren't. And that's, yeah, that's something that I like to do. I really like to think a lot. That's what I do. So, I have a cup of coffee. And I've already had a cup of coffee this morning. But now I have a second cup of coffee. Right here. Inspiration Basic. Why am I pointing to my... Inspiration Basic. It's not a mirror. It's like a video of myself that I'm able to look at. Inspiration Basic. If you guys want me to reopen it, if you want me to open it back up to the App Store again, it only costs me $100 for a whole year for like an Apple developer account or whatever. It only cost me $100. Now this app that I made, I released it in 2014. It lets you code using menus. Okay? So you can kind of select little items in a menu, and you can select like, hey, I want to print this integer. Hey, I want to print this string. Hey, I want to do a while loop here while n is less than 100. And then you can kind of code it so that it solves problems. It sorts numbers. It does things like that. I can re-release it, but Inspiration, which is supposed to be like Inspiration Lisp, is an app that contains Inspiration. Why am I pointing that way? Okay. It's an app that contains Inspiration Basic. And it also contains a lambda calculus editor and a Lisp editor. Now, it doesn't contain all of the program, like, all of the language of Lisp, like the entire documentation of some version of Lisp. It's just meant to contain some subset of it. And I like working with subsets of languages because usually when people add features to a language, they change the grammar of the language. They change the inference rules of the language. They make the language harder to deal with mathematically. So think of it as like an API to the language. I don't like working with a programming language as defined in a book, unless it's specifically designed to be this type of language, but I like working with subsets of programming languages that are essentially APIs to those programming languages, if you want to think about it that way. So it's like I like to interface with the programming language not from a user's point of view, but from a coder's point of view in some sense. So a subset of Lisp is really an interesting thing to work with because it's good at referring to itself and dealing with itself as data. It can treat code as data and deal with that in a more proper way than other programming languages. Whereas other programming languages like they only deal with themselves from a compiler's point of view. They only deal with themselves where if they can see code as a string, which to me is extremely bad. That's extremely limiting, and it's extremely poor because it's you can't prove mathematical properties about a string until you compile it, and you can't compile it until you're running your program, which is already running, so you can't prove things about it. So yeah. Yeah. So, but there is the argument that can be made that if you are able to come up with a higher level logic system, then you should be able to define that in a compiled program, and then therefore your compiled program should not actually get more complex, which is kind of a good argument. But the problem is that we're doing this on an operating system which is running, and therefore we're technically editing input and output as we edit code in the first place. So if you guys don't understand everything I'm talking about, it's okay. It's okay. Don't be like, oh, I don't know. I feel like I should understand everything I'm talking about. If you haven't specifically studied things like programming languages, things like the halting problem, Russell's paradox, Gödel's incompleteness theorem, Turing machines, finite state automata, push-down automata, things like that. If you haven't studied those types of things, graph theory, programming language design, compiler, algorithms, if you haven't studied those things specifically, it obviously it's going to be hard to understand some of the things I talk about. And that's okay. I didn't know any of this stuff before I took those classes. I mean, I thought about some of these things, but I didn't know it nearly as well. And I didn't know what had been researched and tested about the things nearly as well. Until I took some of these different math classes and these different compiler classes and things like that. In fact, before I took a compilers class, I thought compilers were extremely boring and I didn't really want anything to do with them. I just wanted to come up with some mathematical language way or grammatical way to combine things like neural networks and genetic algorithms and things like that. But I didn't really know too much about how much that was done with proofs and formal proof theory and things like that and grammar and programming language grammars. I didn't know that. I thought C++ and Java and these programming languages had really super well thought out designs, and they sort of do, but they're not what you think. It's not what I thought. I thought that anyone who made a programming language knew like all the possible advantages and disadvantages of every possible decision, and that it wasn't really necessarily true. It's not. The people who make a programming language don't necessarily know the mathematics related to programming languages at all. I mean, seriously, it can be really scary how poorly some of these widely used languages actually have certain properties that they don't really have to have, and such as like null pointer exceptions. it's almost insane, like how much you can get away with in industry if you just make something that seems like it works and functions and it seems like it's useful. That's almost all you need sometimes to get something going in industry. You don't need to have any math behind it at all. Even Haskell is like super considered super nerdy, super mathy, and yet they didn't even formalize any of it as they developed it. They didn't even. It's based on some ideas, but it's even Haskell itself, which is considered like the king of nerdy formal languages, is not even itself. It's not even. It itself is considered a practical language. It really is. So it just, I learned a lot when I was in school, and I really liked it, and I could tell that some of my professors even did not know or think about some of the things that I had. So you start seeing a difference between you and some of your professors on things that you know that they might not even know yet. They might not be aware of, or they don't think that way. And you can start becoming aware of, even just as an undergrad, you can become aware of things that even your professors don't know, which is okay. I mean, that's what happens. That's what happens when you become an adult. You learn things that you would think that everyone knows, but they don't. And you have to somehow deal with that, and you have to be able to communicate and try to communicate that. And it's hard, and you'll get rejected for being misunderstood and things like that. So it happens. That's life. So that is my thought. I think I'm going to call the video. I don't believe in clean code. Yeah. And I will talk to you guys later.